So how much progress have we made in AI since Alan Turing? If you believe what you read, you think we've made huge progress. There are front page stories about AI in the New York Times all the time. Scientists see promise in deep learning programs. Wired magazine doesn't seem to publish articles without mentioning deep learning anymore. There were, I think, 4 in the last 12 days or something like that. In some domains, there really has been exponential progress, just like Ray Kurzweil promised you. You can look at data for chess, which is something that's very measurable over time, and programs from 20 years ago were easily beaten by programs from 15 years ago, or easily beaten by programs from 5 years ago, and so forth. There may be a little bit of an asymptote, but in general, there's been exponential progress there. But how about in strong AI, an AI that's really intelligent enough to have human-level understanding, what some people call artificial general intelligence? Well, there are no data there, so I made some up. And what I have plotted here are Eliza and Siri. For those who know their AI history, Eliza was the predecessor to Xiao Ice, the first program that people may have declared their undying love for, and Siri is just one of the more recent ones that people have declared their love for and also gotten sports scores from. But the technology for Siri is not really that different from the technology for Eliza, and Siri is still very far from artificial general intelligence. I love this quote from Peter Thiel. We wanted flying cars, and instead we got 140 characters. There are analogies in artificial intelligence. We wanted Rosie the robot, and instead we got Roomba. This, if I can get it to play, is a video of a robot that can actually sweep the floors. I have 2 small children, as I'll maybe mention. I would love a robot that can sweep the floors, and this one really can. But there are some catches. The movie is actually sped up by a factor of 20. The environment is very carefully controlled. It's not a real home with actual children or pets or anything like that. Oh, and by the way, did I mention that the entire thing is partly teleoperated by a human being? So we still have some work to do. The old school people in the room will remember that AI has died a few times, or nearly died, I should say. There's what people have called AI winters. The first of those was in 1973. There was a famous report in Britain called the Lighthill Report. It said AI only worked in narrow domains. It was unlikely to scale up. It would have very limited applications. It basically led to the end of funding for AI in England. And as I said, it was the first AI winter. Current systems are still narrow, and people talk about how AI is so much better, but it's good to keep a little perspective here. So we have chess computers that can't do anything else. They can't play Go. They can't play Jeopardy. They certainly can't balance your checkbook. We have driverless cars that can't even do it. They can't do anything else. They're totally specialized to that. In fact, they can drive in Palo Alto, but they can't drive in Manhattan. We have language translators that can't answer questions about what they're translating. AI is still basically a collection of idiot savants. Siobhan is right that these are becoming more and more useful, but they are still fundamentally idiot savants. You compare this to your average teenager who can pick up a new video game after an hour or 2 of practice, as opposed to like 30 years of some research team building something. And then you say, oh no, I read the news. I know about DeepMind. They had the Atari game player. Google paid 400 million pounds for them in 2015. It's powered by a technique called deep reinforcement learning that merges reinforcement learning with deep learning, and it's better than humans in 50 Atari games. I saw it in Nature. It's all the problem is solved. But really, not quite. The games in DeepMind system can win are mainly first of all, the low resolution, that's not controversial, and I would call them Brainstem games. They're the kinds of things that you play by reflex, the things like Pong and Breakout and Space Invaders. There's still been very little progress in building a general game player that can play games that require strategy or insight, complex 3-dimensional graphics. Machines can beat human reflexes. That's not really news, but they still can't match human beings in judgment and learning new things and so forth. True AI, or strong AI, would master a wide range of tasks and be able to do things like read Wikipedia and comprehend it and be able to learn for itself. But we're not there yet. We're not even close. And all this is a shame because I think smart AI, if we could ever get there, would help us enormously with medicine, with technology, with science, and also, by the way, make a ton of money. I asked Peter Norvig, who at the time was director of research at Google, I said, how much money would it really be worth if you could have strong AI? And he wrote back about 5 minutes later, suddenly I'm much louder, I think, and estimated something like a range of $500 billion to $2 trillion a year. There was since a McKinsey report that came out that I think came out with similar numbers, but it wasn't quite as impressive as Norvig doing this in 5 minutes. The numbers were similar. So why is AI stuck? If there's so much money to be made and people have been working on it for over 50 years, by the way, always saying that it's 20 years away. They said that in 1957 and they say it now. Why is AI stuck? And I have a 3-part diagnosis, which is that it's fallen in love with statistics, it's fallen in love with big data, and it's forgotten its roots. So consider Google Translate. It's a beautiful piece of statistics, and this is from the first paper about Google Translate. It was about a decade ago. It scales with data. You give it 75 million words in your corpus, and you get a certain percentage correct, and the point was you give it more data, it just gets better and better. You don't need a sophisticated algorithm, you need a lot of data. I, however, was a student of Steven Pinker. I studied psychology and cognitive science in graduate school, and I know enough to read the y-axis. I hope most of you in the room do too. The y-axis here does not run from 0 to 100, as I was taught, but you can rescale it if you want, and then you see a rather different effect of having more data. That was 2005, but things haven't really changed that much. I gave a version of this talk, a predecessor of this talk in Dublin, so I wrote a sentence that harkens back to Noam Chomsky, who's the most famous linguist who has argued against statistical models of language. And the sentence was either the translation of sentences with complex sentence structures into Celtic languages remains remarkably difficult, or it doesn't. I'll leave it to someone else to pronounce the Gaelic later. But it comes back as this: either continue the translation of sentences with complex sentence structures, Celtic language is remarkably difficult, or doesn't. Like, all the words are kind of right, but it's garbage. The technical term in linguistics is word salad. We still have a long way to go in something like Google Translate. I wrote an op-ed some of you may have read, some of you may have cursed under your breath when you read it. It was most emailed to the New York Times with Ernie Davis. It was called, I think, 8 or 9 Problems with Big Data. That was the title that the Times gave it. And I didn't do the graphics. I did the writing in the piece, but the graphics I thought were in some ways even better. It said how often a certain thing happens, how often some other thing happens. And the fundamental point is that big data is a lot about correlation, and we know that's the correlation without causation can lead to a problem. We have similar problems that afflict deep learning. So deep learning is the technique that people talk about most. It's the one that Wired keeps mentioning. It's better than human performance in things like recognizing dog breeds that are very similar. It's revolutionized speech recognition. People do speech recognition in a different and better way now. But there's still problems. So for example, this paper came out last year showing that it's easy to fool these systems. So the system we'll call that pattern of yellow and black stripes, a school bus, lots of kind of bizarre answers. People in the field like to say, well, humans are subject to optical illusions, and this is just that. I don't think this is optical illusions. I think this is hallucinations. It really starts to worry you when you think about using this technology. Military applications, don't worry, killer robot. This is one of the materials. A friend put this t-shirt together. I'm the only one in existence. Don't worry, killer robot. I'm really just a starfish. So it's still pretty easy to fool these systems. There's a general problem that I call the long tail problem. I'm not trying to invent the name, but you have lots of corpus data for whatever you're trying to do. If you're trying to do machine learning, we're talking about Crowdflower a moment ago. You have lots of corpus data for common examples, but you often have little corpus data for less common examples. And the rare examples are really hard for the techniques that we have today. People get very excited every time there's a new deep learning result. But it's always the case they're doing better on the high frequency data than the low frequency data. So this paper got reported in the New York Times, and it's a paper written by Google. A person riding a motorcycle on a dirt road system looks almost like magic. Like, how did this AI system that doesn't really know about motorcycles or roads manage this? Well, the way it manages is most of the things that have brown in the background and a motorcycle in the front get that description, that caption looks great. But it makes me think of an Oliver Sacks thing if you look more closely. You all know the man who mistook his wife for a hat. You should read it if you haven't. Well, here's the program that mistook a street sign for a refrigerator down here in the bottom right corner. So when you start to look at the errors that these things make, they're not human-like errors. And again, they seem almost like hallucinations. No, I don't see a refrigerator down there. I think it's a no parking sign with a lot of stickers on it, something like that. And you can imagine people are working towards comprehension. I'm actually trying to develop a successor to the Turing test, which I can talk about in discussion. But it's an easy question for the one of these AI systems to say, what is the man carrying? A horse. It's a lot harder for the average deep learning system to say, why is this scene unusual? So where I think we should start looking for clues, in a nutshell, is children. This is, of course, my older son. The picture was taken when he was about 2.5 years old. He's now 3. I'm going to show you some footage from today later. I got a text message from my wife. I was away giving a talk, and she said to him one morning, which of your animal friends will come to school today? And he said, Big Bunny, and he gave an explanation for it, which was that his other animal friends, bear and platypus, were eating. And then, sure enough, my wife went into his bedroom, and he had made a little diorama with these other 2 animals who were busy eating. So why is this interesting, aside from the fact that it's my kid, which makes it very interesting to me? Alexander, at this point, understood complex syntax. So in 2 years of training with no labeled data, he had managed, or 2.5 years, he had, I guess I don't need to say more in this crowd. He's doing logical reasoning. He has novel answers that depend on recent updates to the state of the world. The slide I dropped, by the way, was a kind of Facebook thing where it says, Obama said last year he's 53 years old. This year he says he's 54 years old. Which is it, Obama? And the point is, if you have human-level intelligence, you can make sense of that. But if you just memorize stuff off the web and do information retrieval, you could actually get stuck there. He doesn't. So some of you may have seen there was an article in Technology Review about me and my company about a month ago called Can This Man Make AI More Human? So that kind of brings me to the present. My history has been doing cognitive science at NYU and earlier with Steve Pinker at MIT. I formed a company called Geometric Intelligence. We've been pretty quiet about what it is that we actually do, but there's a little bit about us now up on the web. My co-founder is Zubin Garamani, who is a postdoc with Jeff Hinton and a student of Michael Jordan, not the Michael Jordan of basketball, but the Michael Jordan of machine learning, who's very well known at Berkeley. And Zubin is my age exactly. We were born on the same day in 1970. And for a while I was ahead of him. I started graduate school a year before him, and I was 19, he was 20, so he was a slacker. But now I'm the slacker because he was recently named a Fellow of the Royal Society, which is pretty impressive. Our goal is to redefine the boundaries of machine learning through innovative patent-pending techniques that learn it more efficiently from less data. And fundamentally, we're interested in how it is the kids manage to learn so much from so little. So our inspiration is human cognitive psychology. We're pretty well funded from CEOs of Dropbox, Quora, Yelp, and so forth. And we're focused on the problem of sparse data. And there are a lot of places where this problem comes up. So, you know, we live now in an era where people think data are cheap. But whether you have sparse data or not is really relative to a particular problem. So if you think about language, there's actually an infinite number of sentences. That's what Noam Chomsky has been arguing for 50-some years, and I think he's absolutely right about it. Semantically annotated data are very expensive. So why is speech recognition easier than natural language understanding? It's partly because the data are cheaper. You can have somebody on Amazon Turk label syllables. What was this person saying in this sentence? It's much harder. You really need a trained linguist in order to get that data for natural language. And so as a result, there is no great machine learning technique in natural language. Let's take another domain, automated driving. It's also a long tail problem. So you can collect as much data as you want in Palo Alto with very well mapped roads and no weather, and that's fine, and the cars drive around Palo Alto with no problem. You bring them to Times Square where this picture was taken in the rain, and it's a whole different thing, which is why you don't actually see the cars here. Anomaly detection. So you can't necessarily, for each anomaly that you're looking for, rely on labeled examples. Somehow the feds in Mexico managed to solve this problem. They noticed some unusual activity. This was in the Times a couple days ago, an uptick in intercepted conversations about grandma and aunt. There probably weren't a lot of labeled examples in their database saying that's a sign that El Chapo is hiding in this resort, but the human beings were able to figure that out and catch him. Finance is really fundamentally a sparse data problem because the financial markets aren't stationary. If they were stationary, if nothing ever changed, then it wouldn't kind of matter how much data you have. But if in the real world, if you have something that can figure out things, sorry, not everybody can hear it, but from the last few data ticks and somebody else needs all of the data, then the person who needs all of the data is at a serious disadvantage. I happened to take these data from something I saw this morning, which was about how much a medallion cost in New York City to drive a taxi. And the price was going up and up and up, and so if you had data up until here and you need a lot of data, then you're going to say it's going to keep going up. If you can make that realization that something's going on quicker, you're much better off. Robotics. The technique du jour is called reinforcement learning. This is what DeepMind used in their systems, and they used a version called deep reinforcement learning. And what they did is they collected billions, or no, probably millions of data points for each game. So what happens if I move my joystick left now? What happens if I move my joystick right? Well, it's very cheap to play Atari games 10 billion times. You don't even have to put in a quarter anymore. You can have a simulator, so it's really cheap. But it's another thing if you import those same techniques into robots. If you have your robots doing reinforcement learning, which is basically trial and error learning, they start knocking over the furniture 100,000 times, you're probably going to send it back to the manufacturer. Never mind what happens the first time it puts your cat in the dishwasher. I don't know if anybody is following the DARPA Robotics Challenge, but you know, the robots still have a long way to go. This is a small data problem, right? The robot is carrying something that's different from the training regime, and it doesn't do very well. Meanwhile, this was earlier today after 10 minutes of practice. I had to show you this. I showed it to Siobhan in the elevator. She's like, you have to put it in the talk. So this is my son. He's 3 years old now. He is not in New York City, if you're wondering why it looks so warm there. That's the sad part of my tale. But he had about 10 minutes of practice, and he somehow just figured out what he's supposed to do to be able to swim around a pool. He did not need 10 million trials in order to get there. I know he has floaties, but I don't think that's going to help the robots. So, bottom line, until we dive deeper into the human mind, we may be stuck between AI systems with really limited flexibility. My caricature of that is Siri, where it has to actually tell you what it can do, right? The Star Trek computer doesn't need a little cheat sheet saying, you might ask me, did the Giants win, right? The Star Trek computer, you ask it whatever you want. The interface is you talk. Siri, you've got to get to know the kinds of things that it does. There's even a website about the top 50 things to ask Siri, one of which is probably, do you love me or not? And then we have flexible systems that really can answer almost any question, but the trick is that they have humans behind the scenes. So Facebook's new M service, which they have not rolled out at scale, has humans on the back end. There's a little bit of AI in there, but it's mostly human beings, which is why they haven't rolled it out for 1 billion customers. They don't have enough human beings to staff the lines to do it, and it's not profitable yet. So the last thing I will say is, if anybody finds this stuff interesting, we are hiring. We would love to have more engineers, people interested in machine learning, and so forth. So jobs@geometric.ai if you care to join us. And you can follow me on Twitter at Gary Marcus. And I think I'm more or less finished on time, which means we can all eat very soon.
John and Jeremy, we indeed towards the end of the allotted time, but does anybody have any question? Yes. Well, we'll take two, one here and then over there.
Hi, a question about the singularity. Does the conceptualization of that concept help you in any way in the work you're doing? I mean, can you give examples specifically over the last 2 years where if that hadn't been formulated, you would have not made the good decisions you did make?
Well, I guess the first thing is I've been reading about this singularity notion for a long time. And I don't think anything significant towards it has happened in the last couple of years. First thing to say is probably that it means a lot of things to different people. But if it means machines becoming smarter than people, then I think we've made less progress than many people believe. I think it has gotten on the agenda that we should have some concern about AI and whether there are risks associated. I've been writing about that in the New Yorker for several years. The first time I tried to write about it, my editor said, you're crazy to write about that. You've been writing all these articles where you seem smart and rational, and if you write about AI risk, you're going to lose that reputation. We had some back and forth, and eventually he let me write about that and also the employment issues. I think they're real. I'm not worried about the Terminator happening next year, because I don't think machines are anywhere near smart enough to reflect on the fact that we use them as slaves. Maybe that can happen someday, maybe it can't. You know, whether they have value systems where that's relevant, nobody knows. I do think even in the shorter term that we have to worry about things like the Internet of Things, where enormous amounts of data are being collected, and there's more and more tentacles from the machines into our lives. So, for example, when we have driverless cars become ubiquitous and they're all networked and so forth, there are going to be multi-car pileups and things like that, maybe because people hijack them, maybe because they're bugs and so forth. And so there is going to be a kind of scaling problem where technology does become risky, as any technology has been, and I think it does behoove us to think about that. But we don't have to tie it to this magic date of singularity. I mean, what is that date? Intelligence is a multidimensional variable. There are many things that go into it. Machines are miles ahead of us in many aspects of intelligence, like fast computation and arithmetic, and they're miles behind us in others. I don't think there's going to be like one special day with this big explosion. They're going to get better and better. It's going to take a while. We should start planning even for before that.
Wonderful.
So,
hold on. Just can you pass on the mic, please? Oh, sorry.
He's got one.
so, yeah.
Oh, sorry. So speak close to it, please.
Yeah. So Roger Schenck many years ago said that if we could just figure out how human beings do something, then we could teach it to machines. And Schenck clearly had in mind a rule-based system as opposed to a statistical system. Where do you fit in this? Because sometimes at some points I thought you were going to say, okay, it's not statistical stuff, it's rule-based stuff. But is it?
It's a very good question. So there's an old tradition in AI, for those who don't know, called symbol manipulation. I've been an advocate arguing that human beings are symbol manipulators in the sense that a computer is. So we can, for example, do operations over variables. I wrote a book called The Algebraic Mind that's on exactly that point. That said, I think that the right thing that we should be striving for is a synthesis of the old traditions and the new traditions. So the old traditions are much better at dealing with abstract knowledge. The new traditions are much better at learning things quickly. Nobody has really put them together. Obviously, that's something on my mind as a CEO of my company. We have some leverage into that, but it's a very hard problem. So I think we can do some cool things there that people haven't done before, but we need probably a lot more people to think about that question of how do you maximize the kinds of things people were trying to do before in the current context. If I can just say one more second, or that's a cell phone, not a sign to hang up, I guess.
It's not like the Oscars.
That's right. There's an old tradition, you might know about, an old project called Psych, which was by Doug Lennett. It's a 30-year project so far, it's still going, to try to codify human knowledge in the symbolic framework. And there haven't been a lot of practical applications to it, and most people think it's a failure. I think there's a lot to be learned from studying it. I think we want to build something like that. I think in the machine learning world, people shy away from having any kind of concrete knowledge. It's all in the statistics. I think we need to go back to that and say, okay, what did he do wrong? Well, first of all, he was very closed about it, so there weren't a lot of people participating. That's probably not a good recipe. Second of all, we didn't know anything about how to manipulate and represent statistical knowledge back in the 1980s when he outlined the structure. We would probably do that differently now. People had to make compromises, hearkening back to the first talk, about power and speed, and now we have better computers. We might do things differently given more memory space and faster speed. But I think we still need to deal with that project. I have something in the CACM, for those who know what it is, the leading computer science journal, on Common Sense a couple months ago. These problems are still really very important if you want to have robots inside the home. How does a machine know, for example, that if I touch this thing, well, you can't really see it that well, that it's probably not going to go flying back to the room just because I touched it. You can do these things with game engines and things like that, physics engines, try to navigate the world. But with a physics engine, I have to calculate every possible molecule in the room or something like that in order to get the answer. Or what happens if I tilt a cup of coffee? You just know that. You don't need to do a whole physics engine on that. There's some shortcuts that human beings make that allow them to do common sense reasoning. Deep learning doesn't seem to be getting us there. The old systems, in some ways, were better at that. We do need a marriage between the two.
All right, wonderful. On that note, thank you very much.
Thank you.